16.
214.
15 to 2. I can count. Is this it? No, that's linear. That's not linear. We don't do that. That's like a question. Help me.
One moment.
Just seconds.
I'll be right.
This is what we're doing.
Yeah, and then the last thing could
Get a finite abelian group. The order can factorize into distinct groups. Now, some of the elements in G have order that is the power of a prime. Well, in fact, all of them have to crop up. So all these primes appear as orders of elements. We proved that in lemma 13.6, I think it was. So when you take all the elements, for each of the primes, you take all the elements whose order is a power of that prime, any power of that prime between 1 and alpha 1, 1 and alpha I, stick them all into GI. Okay? And then what we're trying to prove is that the whole group is the direct product, the internal direct product of all them GIs. That's the claim of this lemma. And we spend some time thinking about what the internal direct product is. Well, you need subgroups. So we proved that each of these GRs, if you just look at all the elements whose order is power of the prime, that forms a subgroup. And then for the internal direct product, you want to show is that when you take products, so you take an element from each of the GIs, you can get everything in G. Yeah, there's nothing left unexplained in the whole group that wouldn't be the form of a product of something whose order is a power of P1 times something whose order is a power of P2, and so on. Okay, that's the first thing. And the second thing is some sort of a kind of disjoint condition. So these groups are kind of independent, these GIs, subgroups. Okay, so when you look at any one of those subgroups, and you look at all the other elements, kind of, that have nothing to do with the GI, then the only thing you can get in the intersection is the identity. Right? And what's all the other elements? Well, it's those guys. So we proved that second arrow, and what was left to do is that first arrow, and I can't remember how it goes. There's probably somewhere here. So we're proving the first arrow. So we're proving that G is G1 times G2 GK. Okay. Now, one of the inclusions is obvious. Which one?
What is that?
Clearly G gap G1 dot G2 dot GK.
What's that gap?
That gap is for clearly one of the inclusions is obvious.
It contains.
Yeah, but which one?
G contains G1 dot G2.
Yeah. Because you're just taking elements of G and you're taking the product, it has to be in G. So what remains is to show that if you have anything in G, you can write the product of these things. So we take an arbitrary element from the group G, and we're trying to write it as a product of elements with the orders we want. So what is the order of this element? Well, the order of an element divides the order of a group. So it divides, the order divides, what was the order of the group? Well, P1 to the alpha 1, K to the alpha K. So it's something like P1 to the beta 1 times P2 to the beta 2, Pk to the beta K. Now, these betas could be 0, but it can't be more than alpha. Absolutely. Could possibly be zeros, some of them. Okay, now this is horrendous. So AI is going to be a number which is defined as the order of G, so that's that, divided by the I to the beta I. Okay. So AI is, you remove the I prime from that order and take the product of everything else. And what is the GCD of all these A's?
I'm a bit confused.
Yes, yes.
Because,
So am I. Don't worry.
okay, wouldn't the order of G divided by Pi to the beta be 1?
No. So when I said, so A1 is going to be that product. Okay. A2 is going to be, you remove the P2, but you take all the other primes and so on. And AK is the product of all those P's, except for the last one.
But why did
That's
you
what it
write
says.
the order of G divided by PIBI?
Because that's how it works. Yeah, there's nothing I can do about that. So, do you understand what PAI is, everybody?
Yeah.
Yeah?
Yeah.
That's what it says. So, well, so a bit confused. So they have no prime in common, these AIs, because if you wanted to take the GCD, it would have to be divisible by a prime, but there's no prime that divides all of these AIs, because there's always one missing in each of them. So the GCD can't be anything else than 1. And the GCD can be written as a combination of the AIs. So these are some whole numbers. I think we did the same trick last week as well. So 1, the GCD, is equal to A1B1 plus A2B2 plus AKBK, because every GCD you can write this way. And but then, what is G? Well, G is G to the 1, is it not?
It is.
So it's G to the A1B1 plus A2B2 plus AKBK. So this is G to the A1B1 times G to the A2B2, G to the AKBK. not scary. Okay, now, what is the order? What is the order of G to the AIB? Well, G to the AI to the power of pi beta I. Yes. G to the AI times pi to the beta I. That's to the b. Well, that's just reshuffling the exponents. Now, what is this? No, that's the order. That's the order of G because it comes from here. Okay. So this is G to the order of G. What is G to the order of G? It's the identity. And what is the identity to the BI? Well, it's the identity. So it's the identity. So now we still don't know what the order of that element is, but we know that it's a divisor of pi to the beta I. Okay, so the order of G to the AIBI divides pi to the beta I, so it must be a power of pi. And therefore, G to the AIBI is in GI. But that is good, is it not? Because we have an element of G1, we have an element of G2, and so on, and an element of GK, and when we times them all together, what we get is G, and that's exactly what we wanted. We wanted, we started of this, so we took something in G, and we proved that indeed we can always write it as the product of elements of the individual GIs. Okay, so therefore, G is also a subset of the product G1, 1. Okay, and it's the proof. Does that now answer your question why I took these things? Well, because it works. Can't see any more profound reason than that it simply works. Okay? So as a reminder of what we're doing, we're trying to get to this theorem in 4 levels. So what we're trying to prove is that whenever you get a finite abelian group, you can split it into a direct product of cyclic groups, and the orders of these cyclic groups are powers of prime. Now, what have we got so far is that lemma, which has disappeared again. So what we have is you can put it into the direct product of some GIs whose orders it doesn't really say anything about, but they're not saying that they're cyclic, right? They need not be cyclic, but they're all PI groups. Each GI is a PI group because it contains exactly the elements whose order is a power of PI. So now the remaining bit is somehow to show that if you have a finite abelian P group, that you can indeed split it into a direct product of cyclic groups. And then once we have that, we'll have the whole theory. So that's the fourth lemma. Everything else goes away. Where are the lemmas? (13.9). And it says that if we have a finite abelian P group, let G be a finite abelian P group. Now what does it mean that G is a P group? It means that all its elements have orders that are powers of P prime. Okay, so among them we choose G and has the largest order of all the elements of G. Okay, and then then G is the internal direct product so the subgroup generated by this element of largest order and some subgroup K. So K is some subgroup of G. So this G is isomorphic to this times that. And that's the lemma I don't understand, so I hope it's right. It's different from the book. Slightly. A bit stronger. So what's the order of G? Seven.
I'll repeat.
Yeah. And now we do induction on this N. So if N is not, then nothing to prove. If N is 1, then G is cyclic, right? So it's generated by some element, and K is just trivial. And that's the base case of the induction. So now assume that the lemma holds for all smaller things than n. Now, what's the order of G must be a power of P, so we don't know what power, so we'll call it P to the M. So if I take any element of the group G and I power it to the P to the M, what do I get? Well, if I put G there, what do I get?
C of A.
Yeah. We get the identity because P to the M is exactly the order of G. But any other element has order which is a power of P, but no larger than P to the M. So if I do it to the P to the M, I always get the identity. Because G has largest order. It's the largest possible order in the group. Okay, and now I choose take an element which is not there, so it's not any power of G, of smallest possible order. I think I've skipped something. So we're kind of assuming that the group is not cyclic, because if it's cyclic, then the claim holds. Just like here. So here for the induction step, we're also assuming that G is not a cyclic group. Otherwise it holds. And we're just proving it for non-cyclic groups. And if it's non-cyclic, then if I pick an element, what the element generates is not the whole group. So I find something that is not in the subgroup generated by G, so I'll take it. And among the things that are in G, but not in the cyclic subgroup generated by G, I look at their orders, and I pick something that has the smallest possible order among them. Okay? That's that. Now,
The smallest possible order, not one.
well, we don't know what the smallest possible order. Well, it's not one. Sorry, wait. Not one. It's not one because one, that would be the identity, and the identity is in that subgroup.
But if if BG is generated by parameter G, how can H belong to G not become like a part of?
Well, it doesn't. So that stop here, and now we're doing the case where it's not. Okay, if G is cyclic, and it is like this, because you can take K to be that, and that's the whole group generated by a single element of it. Okay, which is always the case if the order is actually p to the 1 of some prime. So what we're assuming from now on until the end of the page is that G is not cyclic. Okay? Little g has the largest possible order of all elements in G. Among the elements that are not in this subgroup, we pick little h, which has the smallest possible order, and the subgroup that this little h generates, we call big H. And now we claim that this big H does not share anything else with that subgroup generated by G than the identity. And that's a bit of a nasty claim. So, the order of h to the p is equal to the order of h divided by p, because that is a power of a prime. So if I already do p multiplications, I only have to do p times fewer multiplications to get the identity. And this is less than the order of h. Now, because it's less than the order of h, and yeah, what? So what happens? So I didn't take this HP to be the element of smallest possible order, which is not in that subgroup. Why? Well, because it isn't that subgroup. There is no other explanation for it. H to the P, sorry. By minimality of the order of H. So among the things that are not there, I chose the one with the smallest possible order. This element has even smaller order, and I didn't choose it, so it must have been in there. Otherwise, I would have chosen it rather than H. Yes. Is that a question? Well, if it's in the subgroup generated by G, then it must be some power of G.
How do we know that? So how do you know the order of h to power p equals the order of h divided by?
Yeah, I'm trying to find the smallest power of an element that gives me the identity. Okay. Sorry. So if I take H, okay, I have to take it to a power of P to get the identity, because we're in the P. I have to take it to some P to the K. Okay. If I take H to the P, I've already put, like, I've already done P of them. So if I keep repeating it, I have to repeat it this many times. So Okay.
Yeah.
Now, oh, sorry, I do this p times. So how many of those bracketed things do I need? Well, p times fewer than I needed for h.
Oh, I get it. I get
So,
it. Yeah.
so that thing, I need to repeat exactly this many times.
Yeah, I don't know why that was so low. It's done.
Okay,
Thank you, yeah.
good. Starting to spread that way. How about that way?
Oh, I got it already.
Yeah, so it is really going from that corner.
Sorry, man.
Okay, so where are we? So because it's in that subgroup, it has to be a power of R because that subgroup is all powers of, sorry, a power of G because that subgroup is powers of G. Now, so G to the R, if I do this, to the P to the N minus 1. That's tricky. P to the N minus 1. What am I getting? Well, I'm getting G to the R is H to the P, so I'm getting H to the P to the M minus 1, which is H to the P to the M. What is H to the P to the M? Okay, well, I'm trying to find the order of G to the R. I power it to this number. Because G to the R is equal to H to the P, I get H to the P to the M. And because we already said that any element of the group to the P to the M gives you the identity, this gives you the identity. So the order of G to the R is no more than that. Could be this, or it could be some divisor of it. But it's certainly less than the order of G, which was P to the M.
Why the order is less than G to the power of R? Why is that?
The order of what?
G to the R is less than P n minus 1.
Well, because if I do it to the P to the M minus 1, I get the identity.
Oh, okay.
So I could get it for a smaller power, but I'm certainly getting it for this one. Okay, what does that mean? Well, that means that if I look at everything that's generated by this G to the R, it is not the same thing as what was generated by G, because G generates P to the M things, whereas G to the R generates fewer things. Okay, so it's not the whole thing, and yeah. Okay, so that's one thing. That would be useful later, I think. I'm lost in the details now. Don't ask me any big questions. The order of G is P to the M. We had that. That was the definition of M. Now, G to the R to the P minus 1, so G to the R times P and p to the n minus 1 is the identity, as we've just seen over here. So, this number is a multiple of the order of G. So B divides R. Yeah. Okay. So let the product be S. So R is B times S. And little a is going to be G to the minus S times H. Is this little a in G? Well, no, because if it were, then GSA, which is H, would be in G, which it is not. So A is not in G. What is A to the P? A to the P is, well, what is A? A is G to the that. It's abelian, so this is G to the minus SP times H to the P. Well, what is minus SP? That's minus R. Well, what is G to the minus R? Well, it's H to the minus P because that's what we said somewhere. Times HP, so this is the identity. So A to the P is the identity. Where is A from? Well, A is...
Is the first one not, is that the cross also?
Yeah, that's not there. So better. That's the identity. So now, why is A in H?
Because this is what it is, as you understand.
So H contains an element of order P. So the order of H, little h, is P. Well, because little h had the smallest order. And there's nothing smaller than P. Well, it can't be 1. Okay, this is a really nasty proof. So, So H is cyclic of order P. And if any element of H was in D, then all the elements of H would be in D, which they are not any more. They are not. So the only thing they can have in common is the identity, and that's the other proof of the plate. We're starting anything. Still haven't proved the lemma. Why is little h in? Where is it? Why is A?
The book says. No, but the book says that if you put A to G minus S H, A can't be in G, because if it were, then H would also have to be in G.
Yes, well, I wrote that. Where's A coming from at all?
You could find it. You know, put A equal to G minus F.
Yeah. Oh, yes.
Yeah? What?
I guess.
I'm confused.
Yeah, so there is an element of G, which is order P, which is not in that order.
There is an element of G which is order P.
Yeah. So now we were choosing this. Remember, we were choosing this, which was not in there.
Mm-hmm.
And it had the smallest possible order.
Mm-hmm.
And we found something that has order P, which is not there. So the thing of smallest possible order, which is not there, must necessarily be of order P. There are some things. Okay, yes, now I understand it. Any more questions?
Do you have any more questions yet?
How long does it take to approve everything? So a lot from you. So where, well, I don't know. So where does it go from here? Now we've got, we haven't got much, right? So we still don't know what K is.
I don't really know why it's running this thing. Why should we learn it? There's no point in it.
Well, it's an exercise.
This is how we actually learn.
Yes, Brad.
Yes.
Basically, we're proving a load of little bits to get to one theorem that we're going to have to be able to use.
It's a bit boring and it's got nothing to do.
Now what's that doing?
Disinterested. So we'll finish it, no matter what, we'll finish it tomorrow.
Yeah.
And then we'll do something more interesting.